this bit. Okay, just that. And then you can think about how to prove the upper bound if you want. There are no hints or anything, so you can just think about it. It's a little bit more complicated, but maybe you can also do it. Okay, so the upper bound. So those bounds are essentially tight, the bounds at the bottom. Not for the same graph, but if you pick different types of graphs, sometimes the lower bound is tight, and then sometimes the upper bound is tight. You can make the 4 go away and make it a little bit smaller, I think. So there's some things you can do to improve this, but it's kind of the right flavor of result, okay? So it's basically telling us that lambda 2 controls the sparsest cut, okay? The bigger the lambda 2, the bigger the sparsest cut is the message of this. Okay, so I'm going to need your help to prove it. So we're just going to prove this one little piece, okay? This lambda 2 is lesser, so our theorem, so we're going to prove that lambda 2 is less or equal to phi g. And remember what phi g is, it's over here. It's the minimum of all the phi s's as you vary over the s's. Right?
Bigness of the sparsest cut is a good thing or a bad thing?
Depends on your application. If you want to make sure that everybody has electricity after an earthquake, big is good. Right? It's saying the weakest connection is not that weak. But if you want to, like, cut off, if you have some other thing that you don't want a lot of connection between two groups, then a small one is good. If you don't want it, right?
It's a COVID or pandemic time.
Exactly, exactly. So if you're trying to isolate communities from COVID, example, good example, then yeah, then we want a small. Depends on your application. Make sense? Yeah. So you can also do this to do things like, not quite sparsest cut, but you can, I was telling somebody about this before, like in computer vision, when people do segmentation, so you have a picture and you want to isolate the background from the foreground, that's called segmentation, cuts out the thing. It's basically a cut problem. So what they do is they think of all the pixels in your photograph as nodes, and they connect pixels together if they are similar, right? So if I have a sky and I have a ball in the middle, then the sky, all the pixels in the sky will be like highly connected because they're all like roughly blue. And the ball will be, let's say, red. They are highly connected. But between red and blue, there are very few edges, right? So you look for, so to cut out the ball from the sky is a cut problem. Make sense? So there's a lot of practical uses for these things. If you have like some surfaces and or, I don't know, molecules, whatever, and you want to know like which are the big pieces, then you can also look for where these weak links are, right? It's very important problem. And there's a lot of amazing results on cuts in general. This is the sparsest cut. People look for minimum cut, maximum cut. Minimum cut is polytime. You can find it in polynomial time using linear programming. Max cut is NP-hard. Finding the biggest cut is NP-hard. Sparsest cut is also NP-hard. It's a similar thing, but it's this thing, what we defined. Okay? So you look at the ratio, it's a ratio. Some people call, and there's something called conductance, which is also similar. So it's sort of controlling information passage through networks, right? Okay, so let's prove that that one piece. So maybe, so let's do a couple of exercises, okay? So maybe the first thing, can you check that. So we're going to use this QX, okay? It looks a little bit unrelated right now, but you saw that it was related, right? So what we did see is that when you take QX, Q and stick in the characteristic vector, you actually get phi s. This is true for all s, okay? So there's some relation between so of course, if I just take all the characteristic vectors and find the minimum of this function, this rational function, I can also get phi g from that, okay? So that's the relationship. And remember, this thing is only defined, as Arvind pointed out, on non-constant x's, right? So this is only defined for all x that is not non-constant. So that means it's not a multiple of 1, 1, 1, 1, 1, okay? So can you check that, can you check this, that qx is equal to q of x plus any multiple of the all ones for all x non-constant. Okay, so please try. Here is the definition of qx. Stick in something that looks like x plus a multiple of 1. And then see that we don't need that multiple of 1. You can basically crash the domain down to the orthogonal complement of 1s. That's what we're aiming for. Okay? So it's just algebra. If you just stick it into this definition, here's the definition. So just check that for a minute. Sorry? It's easy?
Yeah, use the second.
Okay, you can use either one. Is that okay? So how do we use the second one?
It's a plus t and j plus t.
That's right, that's right. So if I add a t times t to every coordinate, then when you do this subtraction, the t just cancels, right? There'll be a xi plus t minus xj plus t. The t and minus t will cancel. So I don't really need adding the multiple of 1 doesn't do anything. Okay? All right, so that's the first thing we check. So this means, and so essentially we're using the fact that either you can do it like that, or you using the fact that 1 is in the kernel of L. That's what, if you use the thing I put in the box, then that's what you'd be using, right? Every time you see 1, you get that. Okay. So this means that we can just, so here's the all ones vector, and here's the complement. Okay, so if I take an x like this that's in the complement, then that's non-constant, right? It's not a multiple of 1, it has pluses and minuses in it. And so we can restrict the domain of the qx to this orthogonal complement. Do you agree? Because everything in space is something in this shaded piece plus a multiple of 1s, right? That's everything in space is like that. So I can just crash down an arbitrary v down to the complement, right? So we can just focus on that. So this tells us that it's enough to compute qx on 1 perp. Okay, so 1 perp is the complement of the all ones. Good? Okay, very good. Okay, so that's the first check. And then the next check we want to do is, okay, this is neither Hebrew nor Urdu now, I'm going to switch over there. Okay, so, all right, sorry for the mess, but we're going to continue here, okay? So can you check too that if x is orthogonal to 1, okay, then the denominator of the qx function, can you check what this is? So I claim this has to be this. So try that. Okay, so we're already in the orthogonal complement of 1. We said that's enough. Now, if I pick something from the orthogonal complement of 1, I want to evaluate this denominator. And I claim the denominator of this is just n times the norm of x squared. Can you plug it in and see that it'll work? This one? So you could use what you just did in the exercise, right? This Laplacian is ni minus j. This might be helpful. Okay, so if you use this, this was the exercise we did at the beginning. So use this maybe in here. And you have to use that 1 is in the null space of L. You can talk to your neighbors, it's totally okay. There's no checking.
So you want us to prove that? Or
Yes, let's prove that piece. Okay, just that piece. That if you take the quadratic form of the Laplace, from the Laplacian of Kn, that's just that. It's just algebra. So you take this, and then you do x transpose Ni minus j, x transpose, okay? X, correct. So this is equal to what? N times x transpose x minus x transpose jx. Yeah, so this is 0, right? Because the j's have all the rows of j's are 1, 1, 1, 1, 1, and x is already orthogonal to 1. So that part is 0. So you just end up with n times the norm of x squared. Good? Okay. So we have these two pieces. And now, okay, so let's use this to check what happens. So if x is orthogonal to 1, then let's assemble all of qx together. Okay, so I want to look at all of qx. So all of qx from that definition up there is n times x transpose lx, right? Divided by this nx square. Everybody okay? Because we just calculated that the denominator is n times norm of x squared. Yeah? N and n cancel. What do we have? We've seen this guy, right? It's the Rayleigh quotient. So this is the Rayleigh quotient of L with respect to x, or x with respect to L. I forget which way I write it. Okay? That's the Rayleigh quotient. Good? Okay. Great. So that's one conclusion. So what we had is this bit, right? So what we knew is the relationship between qx and the thing we're looking for is this. It tells you that if you use these characteristic vectors and plug it into Q, I will get exactly phi s. This is something we know, okay? Now, x complement to 1 is basically all non-constant vectors, right? It's all non-constant vectors. These are also non-constant vectors, right? These are 0, 1 vectors. These are also non-constant vectors. So let's see what we need to do, right? So what happens if I minimize? So I'm still in this situation, okay? X is orthogonal to 1. So if I minimize qx over all x orthogonal to 1, okay? That's the same thing as minimizing the Rayleigh quotient over all x orthogonal to 1. And this is lambda 2 by Courant-Fisher, okay? This is lambda 2. Okay, so this is saying that minimizing, so in other words, lambda 2 is the minimum of all x orthogonal to 1. So I can also write this as, okay, so let's write it this way. So remember this, we decided sometime long ago there that we only need to evaluate qx on this thing. So this is the same thing as minimizing qx over all non-constant vectors. Right? Because if I have a non-constant vector, what is happening? It is something that's, or rather, did I do something wrong? Okay, maybe this part didn't work out.
actually, it is the same as over all vectors, right? X plus t1 and qx is same.
Right.
Then we should get that lambda 2 equal to phi.
No, yeah, so there should be an inequality coming. So let's look at that inequality. Maybe I got confused here. So what did we do? So we have qx. So I need your help to finish this. Let's see. So we have qx.
But this is qx.
Yeah, this is qx.
We only need q of chi s.
Yes, we need q of chi s.
So this is, we are minimizing over a larger set.
We're minimizing over a larger set. That is the point, right? So these are all vectors orthogonal to 1. And chi-s's are...
You can always translate and make chi s orthogonal. I mean, you can always add something.
No, actually q of x is also equal to q of x plus t1. So
Correct.
that means over all vectors, it's the same. It's giving us lambda 2.
Correct. But
Yes.
That would mean chi s would be inferior.
So I want this to be...
But this value will be smaller than possible values of. It's okay.
It's okay? All right, what should I do?
So,
This is okay, right?
yeah, this is correct. So now we are saying we want phi g.
Yeah,
Phi g is min over q of chi s alone,
yeah, that's right, that's right.
not q of all x.
Right, so phi g is min of q of chi s over all s,
Yes.
okay? And min of, and that is
That is bigger.
bigger than, because this is a larger thing, right?
Yeah.
This is bigger than this, which is actually lambda 2.
Yeah, you'll have to translate.
Yeah, you'll have to translate, exactly.
But as you said earlier, you can move any vector to this orthogonal complement by translating the term.
That's true, that's true. So maybe I need to, so there's something here we should write to be fully right? So this chi s is some 0, 1 vector. It is not a multiple of 1, but then I translate it using a multiple of 1 to the orthogonal complement. Okay, so there is a little piece left here, but this is then graded. So this is a much bigger space. So I guess we should write this as qs, which is equal to q of xs plus some t times 1, chi of s. I don't know which one, so let's call it ts1, okay? And this we can do, and this will be greater than if I take, so this is now in the orthogonal complement. This is in the orthogonal complement by translation. And then we are saying, okay, instead of just looking at these special vectors with ones added to it, I just do it over all vectors that are in the orthogonal complement, so the minimum can only be smaller, but that's the Rayleigh quotient, and that is lambda 2. All right. Should we do this again? Is this confusing? Okay, it's confusing. Okay, let's try again. Is this okay? Right? 5G we said is the evaluation of Q at these chi-s's. Okay? So these chi-s's are just some discrete vectors, right? They're these 0, 1 vectors. They're all possible 0, 1 vectors. They're the vertices of a cube, except the origin and the 1, 1, 1, 1, 1. Right? That's what these chi-s's are. So if you evaluate Q on just those 0, 1 vectors, you get exactly 5G. This we proved before, okay? So now we want to expand the domain. So instead of looking at just this small collection of 2 to the n minus 2 vectors, I'm just going to expand its domain. So I'm just saying, okay, I take one of these chi-s's and I can add any multiple of 1 to it so that 1 or minus 1, right? The multiple can be plus or minus. I can do that in such a way that, so every vector has that picture, right, which I erased now. But if I have a vector, some arbitrary vector, so maybe this was my chi-s, like this, I can crash it down onto the orthogonal complement by subtracting a multiple of 1s, right? It has some, I can crash it down. So the evaluation here and the evaluation here are the same. That was part 1 of the check, right? So I crash it down to this thing from the chi-s, and that gets me, that's what I'm trying to write here. This is the crashing, okay? So chi-s is the same as crash down chi-s. But this is now just something that lives in the orthogonal complement. So whatever this is, its value, the minimum value over these finitely many things is going to be bigger than the minimum value over the entire complement, right? The space is much bigger, so it's bigger than that. But this we calculated is just this. Okay, that qx over x perpendicular is just the Rayleigh quotient, which by the other exercise is lambda 2. Okay, so that's the lower bound. That lambda 2 is less or equal to this sparsest cut. Okay, the density of the sparsest cut. Okay, so this is, I think, the proof that's reasonable to do in class. The other one is a little harder, but you can try this at home if you like.
Means, ma'am, all one vector is eigenvalue of n.
Yeah.
And sorry.
Eigenvector.
So in minimum x perpendicular to 1, we are taking all the other eigenvector or spanning vector of all other vectors.
Yeah.
But here we are taking any vector that is their sum is 0.
Yeah.
That is not restricted to the eigenvector and all that.
No, it's not.
So this is why it is bigger.
Yeah. So it is, exactly. So this perpendicular thing, this is an eigenspace only for the complete graph, right? For arbitrary graphs, it's where all the other eigenspaces are. But it's not the whole thing, right? It's some decomposition of that, exactly. Okay, so if you're feeling ambitious, you can try the upper bound later at home. Good? Okay, so
Still have time. So are you planning to say something more, or do you?
I was going to talk about the bipartite graph as the last thing. Okay, is everyone tired? Okay, so I have one more thing that I prepared to show you. So okay, why are we doing this, right? We're trying to just understand why would you compute these eigenvalues and eigenvectors of these matrices, like what good is it? So I'm trying to convince you that there is good. Hopefully I've convinced you a little bit. So lambda 2 is useful for checking connectivity. It's also good for clustering. Okay, clustering into two parts. But there's like infinitely many things that you can read about spectral graph theory. You can ask all the experts, yeah.
Is this clustering thing is applicable to AI or machine learning, that kind of thing? Because sometimes machine have to know what is difference between like sky and one ball.
Yeah.
So if it's helping to that way?
Maybe, I mean, typically things in AI and machine learning and so on involve millions and millions of points, tremendously large graphs. So you have to have clever ways to compute if you want to like take the whole graph, right? But that's typically not how neural nets work, right? They have data, they learn the data, and then they spit out the model. So yes and no. Yes, I would say there is use. Oftentimes you also have a mix of algorithms. It's not one clean algorithm, right? You try many different things, you hit it with, and then at the end of the day, you've improved the thing by like 2% or whatever. So it's good to know the pure pieces so that you can plug it in as needed. But I don't know a lot about AI, so I don't know exactly. But I would think it's useful because there are these things called graph neural nets, right? So graph structure is very common in large data. Like social networks are all graphs, right? Like if you want to understand what Facebook is doing, or Facebook graph is a very famous one. Your brain is a graph, right? Like we have like 10 billion 10 billion nodes in the graph of the brain with neurons connecting them. So if you do surgery on a tiny piece of your brain and you want to know, will it now mess up this other part of my brain? It's really important to know the structure of this graph, right? So there's a lot of use to actually understanding graphs. There's also something called systems biology. I don't know if you've heard of this. This is very big in the US at least. So they want to think of your whole body as a graph, okay? So your brain is connected to your liver, is connected to, the liver is here somewhere. Anyway, everything, right? And then, so instead of like the modern way of Western medicine where you go in for, I don't know, something, they give you a medicine and they don't care how this is affecting your heart or okay, they might check the heart, but they don't know how it's affecting like some other things, right? It's very specialized. You go to a specialist, dermatologist doesn't understand neurology, doesn't understand whatever. So systems biology is a way of thinking of your whole body as a graph. So if you want to, and then this on top of like your DNA structure and so on is going to like bring in personalized medicine, which will like scan you and look at your graph structure and your DNA and prescribe medicine that's specifically for you. So not a generic cancer drug, but a cancer drug that will actually be good for you, right? Because it won't mess up your something else. Yeah, so, okay. I don't know anything much about any of this. I'm just telling you the few things I have seen. But yeah, I think graphs are like the most fundamental combinatorial objects in some way, right? Like everybody knows a graph. But they touch a lot of mathematics. So today we saw how it touches linear algebra. Tomorrow we'll see some probability and other things, some convex geometry. So every day we'll see like different parts of math coming into problems that come from graphs. Okay. All right, shall we do one more application? Or do you want to be done? No. Okay, because no one's going to say no.
If you're tired, you can take a break. You can do something you want to.
Do you know the proof of why the Fiedler thing connects?
Not off the top of my head.
Maybe tomorrow?
Oh, sorry.
We can show them?
Yeah, maybe we can show that.
Tomorrow. So I totally missed that. I didn't even think of it. Yeah. Okay, let's do one more application. Let's prove how you can detect whether a graph is bipartite by just looking at its spectrum. Do you know what bipartite means? Like the graph is split into two parts and the edges only go across, okay? And I claim that you can just look at the eigenvalues and tell whether the graph is bipartite or not. So let's prove it. So that's a application of the largest eigenvalue, okay? These ones were applications of the smallest non-trivial eigenvalue. Okay, so there is homework for tomorrow, which is to, well, one, please look at the exercises. If you haven't done them or don't know how to do them, talk to your friends. Try the exercises, that's good. But the other thing is, since you all have the Mathematica notebook, maybe you can compute one thing that you think is interesting. So take any of the little snippets, run your own graphs, like thousands of graphs in there, in Mathematica, and see if you can show something that seems interesting to you. And maybe we'll share this at some point with the rest of the class, okay? So anything like pick, yeah, you have many, many things you can play with, right? And your Mathematica licenses will end in 30 days?
Yeah.
Yeah, so make use of it. It's a short window that we have these licenses for. So yeah, I think it'll just get you used to actually typing stuff in, and it's fun, hopefully. Okay, so okay, so this is not a very long proof, so hopefully we're done soon. So the third application is how to detect bipartite graphs. Okay, so G is bipartite if the vertex set can be partitioned into two parts. So typically you write it as A and B. The dot on the top means disjoint union. So our graph looks like such that Ij in E implies that I is in A and J is in B. Okay? So typical picture of a bipartite graph will be, here are some vertices and here are some other vertices, and the only edges you see go across. Okay? That's a bipartite graph. You have two parts. So this is like in the stable marriage problem and things like that. You have people here, you want to pair them up somehow, or there's only connection from one side to the other side. So there are no edges within the groups. Okay? That's a bipartite graph. And then the theorem is that a connected graph, a connected G, is bipartite if and only if this is the adjacency matrix eigenvalue, mu1, okay? We're now in the adjacency matrix. This is equal to minus mu n. Okay, so remember in the adjacency matrix, the spectrum this is the largest eigenvalue, this is the adjacency matrix. And then the smallest one is mu n, and 0 is somewhere here, okay? And what we learned is that this one in absolute value is less or equal to that one, right? So Frobenius told you that so minus mu1 is usually like here somewhere, okay? There's mu1, there's minus mu1, and all the eigenvalues are between minus mu1 and mu1. But we're saying that you're bipartite if and only if these two agree, okay? So there's nothing here. So minus mu1 must be mu n. The first eigenvalue is the negative of the last eigenvalue. So again, you can check whether a huge graph is bipartite by just looking at these two eigenvalues. What's the eigenvalue of, if you take the graph of the cube, three-dimensional cube, is it bipartite? Yes? Do you see the bipartitions? Yeah, just take like one side of the cube and the other side of the cube and all the edges go like this, right? No, I'm wrong. No, so wrong. That's not the bipartition. So what is the bipartition?
Antipodal vertices.
Antipodal vertices. Okay, yeah, okay.
Antipodal, just take one out of it.
No, you take all vertices whose sum of coordinates is odd, they form one vertices.
Okay, let's draw it. Yeah. Good. Okay, so if I color this one red, then I got to color, yeah, these are in the other color class, okay, those are in B, and then this has to be red, this has to be red, that has to be red, and this one has to be purple, okay, so it's bipartite. So hypercube graphs are bipartite, any dimension. Yeah, so it's like that. Okay, I think there are, okay, so this is a picture, right? This is a picture, this is what you do. So this is bipartite, the purple is maybe A and the red is B, okay? And there are no edges among the reds or among the purples, but all the edges go from purple to red. Yeah, so it's a bipartite graph. That's not so clear, right? Like when you see graphs like this that are not drawn like this, it's really hard to know immediately if it's bipartite, right? So checking bipartiteness takes a little bit of work. Okay, so let's actually prove this. Okay, ready? So let's actually do this, okay? So what we know from Frobenius is that Frobenius told you that this thing, right? That the mu1 is greater or equal to the absolute value of mu n. So it told you that the absolute value of mu n is less or equal to mu1. This is what Frobenius told us, okay? So the idea is going to be, first we're going to see why that's true, and then we're going to see what happens when you get equality. Does the bipartiteness just kind of fall out of the proof? Got it? So first we'll prove this, which is Frobenius, and then the proof will show us how to construct the A and the B. Okay, that's the idea. Okay, so what we're going to do is we're going to pick, so let's let phi be eigenvector of the last eigenvalue, mu n. Okay, so mu n is the smallest eigenvalue and I pick an eigenvector of it. So this definitely has plus and minus things in it, right? It does, okay? So I'm going to define a new vector y, and this y is defined so that yi is the absolute value of phi I. So take the phi vector and just turn all its coordinates into positive, okay? Just flip the sign on all the coordinates, And now I have a vector y, which is non-negative. Do you agree? I'm going to define a vector, define. Does this make sense? So if phi was like -3, 2, and -1, then y is going to be 3, 2, 1. Okay? So just take the absolute value of every coordinate. So by construction, this y vector is non-negative. Right? Just by construction, it's non-negative. It may have some zeros, but it's non-negative. Okay, so now let's actually try to argue this inequality, okay? So I want to start with the absolute value of mu n. Okay, how is it related to phi? We already know, right? Rayleigh quotient, quadratic form. Can you write that in terms of phi? No, but if you actually plug in the eigenvector into the quadratic form, remember you get the eigenvalue, right? Yeah, exactly. So this is, let's assume phi is norm 1, okay? Because that way we don't have to worry with the denominator. So phi is norm 1. Does that mean y is also norm 1? Yeah? Okay, y is also norm 1. Because all we did was flip the sign on the entries. Okay, y is norm 1. So this is actually phi transpose times A times phi. Okay, we did everything with the Laplacian, but it's the same proof. So this is the absolute value of this. Okay, so with the Laplacian, we argued that if you plug in eigenvector into the quadratic form, you get the eigenvalue. It's the same thing. Okay, so that value, absolute value, is the same as this. Everybody okay? Because I'm using the eigenvector of that mu n. Okay, so now this is, does anyone know how to write this phi like a quadratic form? If you have, you know, x transpose some matrix times x, do you know how to write this as a big sum? Yeah, exactly. So this is mij xi xj over all I and j. Okay? So if you don't know this, you can check this at home. This is actually very helpful. So we just go to the whole matrix, pick out every single entry, mij, multiply it with xi, xj, and then do this for every ij. Okay? So that's what that is. Okay. So now, so this is really the absolute value of the sum of aij, phi I, phi j. Okay? That's what we just did. Right? How is this related? What happens if I now change this to aij, yi, yj? What will happen, you think?
Less than or equal to.
Yeah, it's less than. Do you agree with that? Because the phis had some negatives possibly, y's are all positive, a is definitely non-negative, so you get this inequality. Okay? So this is the first weak part in Frobenius, that you get an inequality. Okay? We get an inequality. Okay, great. And now, that one is, so this is the same thing as y transpose ay. I'm just using that thing again, right? That's y transpose ay. And that thing, do you see by Courant-Fisher how this is related to mu1? So Courant-Fisher exercise was, the second piece was lambda n is the max of x transpose Lx over all x. Okay, it's norm 1, everything is norm 1. So I don't need the denominator. Okay? This was the other exercise. So then what happens in this y transpose ay? How does it relate to mu1, the top eigenvalue? So remember, this is Laplacian stuff. For a, everything flips, right?
Less than equal to.
Yeah, so this is less or equal to the maximum of y transpose ay over all y of norm 1, okay, which is mu1, okay, by exercise. Everybody okay? So that's a proof of Frobenius. We just proved that the absolute value of mu n is less or equal to mu1. Good? Where are the problems? There are two inequalities, right? So in the bipartite graph theorem, we are told that mu1 is minus mu n. So that means absolute value of mu n is mu1. Same thing, okay? So if I make all the if I want to make all the inequalities into equalities, what has to hold? So let's think about that, right? And hopefully the bipartition falls out of that. Okay, so I'm going to give some name to these inequalities. So this first inequality, okay, for some reason I named it in a funny way. But this inequality is A, and this inequality is B. Okay? So let's give those two inequalities. Okay, so let's look at, so the question is, when do you get equality? How can you make those inequalities become equality? So you remember what y is, right? So I'm just, yi is the absolute value of phi. That's the definition of y, okay? Okay, so let's look at A first. Okay, so remember that we saw that if y is an eigenvector, okay, let's not use y, let's use another thing. What can we use? Z? Z? Okay, maybe Z? V? I keep saying Z, so we'll do V, okay? So if V is an eigenvector of mu1, okay, then we know something about it, right? What kind of vector is that? All positive. We proved it, right? Today in the morning. So this implies that V is positive. Okay? So that is positive. So in particular, actually I do want to use Y. So if Y is an eigenvector of mu1, then Y is positive. Okay? I'm just making something up. Okay? So if Y is an eigenvector of mu1, then Y is positive. And this implies, so this is the same Y we're talking about. Okay? So if this happened to be an eigenvector of mu1, then Y is positive. And this implies that phi is also positive. Do you agree? Because we got Y by turning all the coordinates of phi to the absolute value. Right?
Y is always greater than 0.
It's greater equal to 0.
Oh, you're talking about greater than 0.
Yeah, I'm saying that if Y is an eigenvector of mu1, then in the morning we showed that it's actually completely positive, not just non-negative, right? So if the Y that we constructed here was an eigenvector of mu1, then it is completely positive.
Yeah, but that does not imply phi is complete.
Phi is not zero.
All you can say is that it's not zero.
Yeah, it does not change.
I mean, phi I is not equal to 0 for.
It's a non-zero vector.
Not that it's a non-zero.
Oh, I see what you're saying. Okay, you're right. Yeah, you're right. So all I can say is that phi doesn't have any zeros. Okay, yeah, correct. So phi I is not 0 for all I. Good. Okay. Good. Everybody's paying attention. Excellent. So that is the case. Okay. So then, so it's not 0 anywhere, but it definitely has zeros and, it definitely has negatives and positives, right? Phi definitely has negatives and positives. So there must be some edge. So there exists some edge AB where phi of A switches from positive to negative, right? This is like the same kind of connectivity argument that we had.
Just to clarify, are you talking about B or A? Because in A, if you want to make that an equality, by Courant-Fisher, you just want Y to be the eigenvector of U. Right? So there's nothing.
That's right.
So
That's right. Am I not talking about A?
B. Because for A, if A has to be an equality, in Courant-Fisher, Y has to be the corresponding eigenvector of.
That's right. That's right. So to get this equality, where is it? So this.
You're just saying Y transpose AY is equal to the max of Y transpose AY.
Yeah.
But we know that that will happen at the eigenvector,
That's right.
largest eigenvector,
Right.
which we know is mu1.
Which we know is mu1.
So
if y is an eigenvector,
no, there's
Yeah.
no if then. Then y has to be the eigenvector. If A has to be an equality, then y has to be the
Yeah, okay, let's write it properly. That's exactly what I want to say. So what I want to say is that if we have equality, so if A is an equality, implies y is an then I don't need this if, right? So if A is an equality, so with this part, this if you get equality here, that means y must have been an eigenvector of mu1, okay? So A is an equality, thanks Arvind. So y is an eigenvector of mu1, which means from the morning that y is positive, which means phi doesn't have any zeros in it, which means phi must jump from positive to negative over some edge, okay? There's some edge where it jumps from 0 to positive. Okay, so this is the first piece. And now let's look at B. We're almost there. And I'm going to probably get confused again, but let's try. So equality in B. Okay, can you help me with equality in B? It's probably if and only if. Okay, so if I want equality in B, which is here, right? This is where this absolute value trick had to happen, okay? So if you want equality, there's an absolute value here, so that's okay. But it must mean that this phi I, phi j, this is over all edges, right? Yeah, so we need this phi I, phi j to be what? The product. Exactly. So it must be that this product has the same sign as you vary over all ij's, right? Because if some are plus, some are minus, it'll cancel out and you'll get like a strict inequality. So that happens if and only if phi I, phi j has the same sign. So phi I, phi j has same sign for all ij that are in E, okay? And what must be that sign? Can it be positive or should it be negative?
Aij is
Positive. Aij is positive.
yi is a positive, yj is so
But we're taking an absolute value, so it could be that this product is always positive or always negative. That's what we just concluded, right? So my question is it always negative or is it always positive?
since it's an equality
Yeah,
that you're assuming,
but there's an absolute value also.
there's an absolute value.
It cannot be the same sign now, because if it were, then phi would be actually completely positive, because the graph is connected. So
Okay.
I could start with phi 1, it connects to some other edge,
Yeah,
then you say it's the same sign. If it had a positive sign,
yeah.
then everything would have the same sign, starting
From the top.
and the graph is connected, but that would mean phi is completely positive.
No, like for example, if you could have a graph like this with 1, minus 1, 1.
No, but we are saying, right, but no, this is not what we are saying like that. We are saying phi I, phi j has the same sign.
The product.
Yeah.
Yeah.
If that product were positive is what we are
Okay, you're telling me it's not positive.
Cannot be positive.
Okay, say again please, Arvind. I didn't understand.
So, if they were all the same sign, like 1, 2, 3 or whatever,
Yeah.
so that would, starting from 1, then you get something else which is positive, then something else which is positive, etc. You get the whole graph because it's connected.
Exactly.
But that would mean phi is
Positive.
positive.
Yeah.
But that's a contradiction because phi is an eigenvector of mu n.
Of the last eigenvector. Exactly. So it has to be negative. Okay?
Yeah.
So it has the same sign and it's negative. Everybody okay?
There exists one edge variable such that phi is negative.
We're just looking at the products. Okay, everybody okay with this so far?
could you repeat why it has to be negative?
Actually, Himanshu has a good point.
Yeah.
From this point alone,
Yeah.
you can see that this phi A, phi B has, there exists an edge AB, no?
Yeah.
And what is the sign of phi A, phi B?
That's right. That's true. From this, we can already see that this.
That is provided equality in A opposite.
Yeah, we are.
About equality.
No, we want both equality.
We want both equalities.
The same thing.
Correct.
Yeah, because what is the theorem?
Yeah. Right?
One is minus 2.
Yeah. So this is what we want to get to, right? And Frobenius only tells us that this is smaller, this is bigger than this. Okay? We're looking for equality. We see the proof of Frobenius, here it is, and we're forcing, so if we want equality, these two have to be equal. Okay? If this is equal, why you get the first bit, and from here you see, okay, there's some edge where they are different signs, so the product is negative. And then if you want this equality, it better be that all of these signs are the same, otherwise you'll get cancellation, but that sign is negative by the first piece. Yeah, thank you. Okay? So this implies that, okay, that sign is negative. Good. Okay, and now do you see the bipartition? We're kind of done. So this last piece is telling you that anytime you cross an edge, it goes from positive to negative.
Collect all the ones with positive.
Exactly. Put all the positives together and put all the negatives together, and that's the bipartition, right? Because positive can't be across an edge, because the product has to be negative. So across every edge, you will see positive, negative, so that's the bipartition, okay? So all the positives, so collect all the positives together, that's A, collect all the negatives together, that's, so it'll go like that. Yeah, is this clear? So that's, so the only thing we have proven so far, so what we've proven is that if mu1 is minus mu(n), then G is bipartite. So this is only one part. Okay? All right, so we proved that one. Do you see the other piece? The other piece is actually, okay, so for the other piece, I'm going to prove something else. Is this okay? Everybody understood this? So if mu1 is minus mu(n), then the graph is bipartite by this whole argument, okay? So the last piece we're going to prove is that if you have a bipartite, so what I need to prove is the other way, right? If G is bipartite, then this happens. That's what we need to show. But we're going to argue that if G is bipartite, all the eigenvalues are symmetrically arranged. So if mu is an eigenvalue, minus mu is an eigenvalue. And that'll finish, right? Because then if mu1 is an eigenvalue, the last one has to be minus mu1. We're done, okay? Do you see how to prove that? That the eigenvalues are symmetric across the origin for a bipartite graph, okay? So what do we have to actually show? It's kind of a much easier proof than this. So I want to argue that if mu is an eigenvalue, minus mu is an eigenvalue, okay? So claim is that G bipartite implies eigenvalues are symmetric about 0. Okay? So let's pick an eigenpair. So pick mu phi. This is not the biggest or smallest or anything, just some eigenpair. Okay? So let's pick an eigenpair. And I know that the graph is bipartite. So I know that the graph is broken into this A part and this B part, and all the edges only go like this. Okay? So we're given that. So if I want to show that minus mu is also an eigenvalue, do you think we can mess with that phi and produce an eigenvector for minus mu? Okay, so I want minus mu and something, let's call it phi prime, to also be an eigenpair. This is what we want. Do you agree? So the only question is, can we like massage this one into this one? It's not the same, right? It's not the same. It's not the negative, because eigenspaces are subspaces. If V is in there, minus V is in there. All right. Any thoughts?
Adjacency block matrix is it?
Sorry?
If it's bipartite, we get a kind of a
True.
block diagonals are 0 here and
off diagonals will exist.
Yes.
And they will transfer.
Yes. Do you see a simple formula for what? Okay, maybe we should look at an example? You have your Mathematica.
This proof gives the hint.
Yeah, okay. So what do you think this phi prime should be? Yeah, so let's evaluate it at some vertex, right? This is the A part. Say I take an edge like this, AB. Okay, the little a's are in the A part, the little b's are in the B part. Okay, so how should we can we define this in a clever way using this from that proof? So you get.
I think the first part it will take consider that little x. For the second pair, it will take little minus y or something like that.
Yeah.
Just change the sign.
Change the sign. Okay. So if we say this is phi A, if A lies in big A, and if it is minus, maybe we shouldn't call it A, X, and minus phi X if X is in B. Okay. Can you check? It works? So all you need to check is that this vector that we just constructed is an eigenvector of A, right? So you need to check that, it's an eigenvector, you have to check that A times this new vector is equal to minus mu times the same vector. So that's all you need to check. If it works, then you got a new eigenpair with minus mu as an eigenvalue.
Well, it's still not technically complete because
There's more?
there are problem if phi at B is 0, phi is 0 in all of B, then you have a problem. It's the same
Phi
vector.
if 0 is in all of B.
I mean, phi evaluates to 0 in all of the B part, and minus phi is also 0 in that B part.
Yeah.
So phi prime will be equal to phi.
Okay, so maybe you have to check some corner cases don't happen. But I think it'll go through if you check all the little pieces. So you have to actually just calculate, like you have to calculate this. Okay? Yeah, it works out? Okay, Kranta said it works out.
This is what we get.
Okay.
Minus over here, the same equations will get out of this.
Okay. All right. So it seems we have one proof over here. Anyway, think about this. So this is the last bit. This is the last possible. It's not the last possible. It is another application of the spectrum, like why you might care about the spectrum. But you can do a lot of things with the spectrum. You can compute, you can bound chromatic number, you can do many things. So maybe another homework is to just Google and see what are some other uses of eigenvalues, right? Like what can you bound? Chromatic number is the number of colors you need to color the graph so that two adjacent vertices don't get the same color. So that's bounded by eigenvalues. Many things, many parameters of graphs are bounded by eigenvalues, either below or above, or it's never usually exact because most graph parameters are NP hard to find, like the stability number, so it cannot be exact, right? Because we can find these eigenvalues in polynomial time. So it cannot be like but you get bounds from eigenvalues. Okay. So maybe then two pieces of homework. One is to run some Mathematica code on some interesting graphs, whatever you want. See if you get anything interesting. We saw many different things you can compute. And then two is just to look through the exercises and make sure you got everything. We touched on everything in class. But if you're missing something, then feel free to ask tomorrow, ask your friends. And then Google to see what else can eigenvalues do for you. Is that good? Okay, so tomorrow we'll do something new. So tomorrow we're going to talk about random walks, and then from there we're going to get into something called designs, which is I think in the title of the course, right? Graphical designs. So we will define what they are, we'll show they exist, and they're motivated by random walks. Okay?
Maybe we can just
check some of the results that she mentioned, that she has proved today. So I think this Thomason graph is a good example. It has 94 vertices, so it's rich enough. So L is the Laplacian.
Enlarge the size of it.
Sorry?
Enlarge the size.
Sure. Okay. I can't click that button. That's it. Can you see now? Yeah, so this is the Fiedler vector visualized on the Thomason graph, as you said. This blue on this side, red on this side. We can see the specific vector. So let's see. So if I just do Eig. No, so this is not the eigenvector. Okay, so let me just, there's some renormalization here.
Yeah, there is.
So I'll just do this. So you can see that some of the numbers are negative, some are positive, some are very, very small, 10 to the minus 15. Okay, but we can kind of systematically go through the let's see. No, I should not do the whole thing. Okay, so L is already defined, right? So I'm just going to change this slowly. So this is the Fiedler vector. Now you see that signs are more or less the same. Let's go slowly over here. Now you see the positives are both here and here. Let's just assume blues are positive, reds are negative. It doesn't matter, right? It's a eigenvector, so I can change sign. So blues are positive, reds are negative. So it's positive over here and negative over here. Now if I go one more, now it splits in some other way. You can keep going down. Let's go 10. Now you see it's really broken up into many, many pieces here. Red, 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 blue, blue, blue. Okay. So this is one thing I wanted to show you. Should we compute? Can we do the second approximation algorithm?
Yeah, we could on some reasonably small graph.
Yeah, okay, so we can try something like that. So we only have to look at phi 2 anyway, right?
Yeah.
So.
Do you want to check?
That's fine. So actually this is okay, no? I mean here.
I mean this one has a lot of entries.
Yeah.
In phi.
But still, I mean, so if I call this phi. So yeah, let's try doing the second approximation algorithm. Okay, so this is a fairly complicated thing, and now let's do sort phi. I'll just sort phi larger. No, it's not sorting. Or sort by. This is in, we wanted in decreasing, we wanted,
It doesn't matter, increasing or decreasing.
it doesn't matter. And now I have to look at the indices.
Yeah, you have to remember the indices.
Yeah, but this mathematics I can do. I think if I do permutation, the only thing, here. There's a way of doing this, I have to recall. So if I just input one list and another list, which is a permutation of that, it will give me the permutation that takes one to the other. This is what. Find permutation. Yeah, okay, so let's do this. So find permutation of phi sort phi. Okay, so it's giving it in cycle notation, but I have to, I can. Oops. Permutation list, I think. Okay. If I do permutation list of this. Okay, so it gives me this. Let's just check which way it is. It could give either the permutation or its inverse. So 0.00. Okay, let's look at.
I think when you sort it, goes from the most negative to the most positive.
Actually, I think this is a bipartite graph because this number is the negative of this number. These two are negatives of these two. Yeah.
There you go.
Okay. All right.
That's amazing, right?
Yeah.
It's a bipartite graph.
No, it's not bipartite. I mean, there's a. Yeah. Anyway, it's not bipartite. There's a pentagon. Okay. Anyway, so let's check that the largest value. Okay, so I'll just find the index or position in phi of this largest or smallest number. (41). So it's moved the 41st thing to the first position. And but okay. But I think we want the other way around.
Yeah, could be. Might be easiest to write a little bit of code to output all those sets.
Actually, let me just try 1 second. If this works the other way around, sort phi, and I delete this. Okay. So 41 is now the first one. So now we should look, according to you, according to the theorem, at Sk, which is the first k things.
Right. And then for each of those SKs, we have to calculate the phi s.
Okay, phi s.
Pick the best one.
Okay, so phi s was, can we define phi s?
Phi s is that ratio.
Phi s. What should I do it in general or? Oh, I just take the cut. Okay. Okay. So let's take. Okay, let's just take one cut. V is, let's say, 41, 40, 42. I'll just take the first three. And now, how do I find the subgraph?
I don't know.
Subgraph. What was the name for Thomason? G. Okay, so it's taking that subgraph.
But then we need to know the cut edges, right?
Yeah.
So you need to maybe pick the edge list and then look at what is connected to 40, 41 and 42. That sounds
Edge
a
list.
bit complicated.
Edge list of G is this. Okay, and
Yeah, and then anything that has 40 or 41, it's probably even doubled up. Sometimes Mathematica gives you this weird
this is repetition.
repetitions, yeah.
Oh.
But it may not be in this case.
So, but
It doesn't look repeated.
but how do I?
So now you have to pick each piece and check the tail and the head. So if you do edge list,
But how do I mean, what is this data structure? This funny thing.
it's like a pair. So if you do edge list G, double bracket,
One. Yeah. And now if I do.
Now do one of that again.
Okay. And if I do 2, it will get 2, is it? Okay. Okay.
So you may have to write a little loop or something.
Yeah.
Maybe this is good for both.
Yeah. Okay. Okay, I'll try and code this by. So Mathematica has this notation that if you want to, because the functions are evaluated with single bracket, if you want to pick the ith element of a list, you have to put double bracket.
Double bracket.
Yeah, that's a coordinate.
Just go to the first edge.
So here is edge list. If I do the fifth coordinate, so the fifth coordinate should be 2, 9.
Yeah.
So that's what this is.
Exactly. And then if you want the 2, you do double bracket 1 on top of that.
Or maybe I could just do comma 1. Sometimes that works. Yeah, that's also. Or I could do, like Rekha said, I can do 1 again. So I can write a code and I can put it on, on the thing to compute phi of s. Okay, so shall we stop for today? I think it's a long day. Yeah. Okay.